You guys are a great audience. So thanks for coming. My name is Rob. I organize Idea the IPO. We've been holding events in Silicon Valley for many years. We hold events multiple times a week from San Jose to San Francisco. We always have a busy calendar of events. I'd like to highlight two events that are coming up. Tomorrow, Wednesday, September 13th, latest innovations in robotics. We have a great panel lined up. It's at the law firm of Perkins Coie in Palo Alto. Next Monday, top 10 legal mistakes that could kill your startup. That's going to be in this room, featuring Roger Royce of Royce Law Firm. So check out all the details for those events and all of our events on our website, ideaipo.com. We were launched officially on February 1st, 2010. At that time, we had no members and no events on our calendar. At this stage, we have over 55,000 members among all our meetup groups in the Bay Area, and we've completed over 1,787 events. By any standard, by any measure, we're the most active, most prolific startup event organization in Silicon Valley, bar none. Yeah, I appreciate that enthusiasm. Our mission is to promote entrepreneurship, support entrepreneurs, build community, and provide value in the Silicon Valley startup ecosystem. To that end, we provide content that's practical, actionable, and relevant, stuff that you can actually use to succeed as entrepreneurs. We believe in building community because Silicon Valley is an aspirational ecosystem, and it attracts people from all over the world who come here to do great things. And I'd like to know who here is not originally from Silicon Valley. Who here was born and raised in Silicon Valley? All four of you, great, welcome. So whether you were born and raised in Silicon Valley or you arrived last night, it is important for us to provide multiple channels for you to meet people, build relationships, and grow your network. So in addition to our content-oriented events throughout the week, we also have social events on Friday nights. And in fact, we have a regular TGIF mixer, that's thank God it's Friday, and that's hosted by CJ Terrell, one of our team members. I'd like to have CJ come up and tell us a little bit about that event. Let's hear it for CJ.
Hi everyone, hello. Hi everyone, I'm CJ. So as Rob was mentioning, we have these TGIF mixers. They're really fun ways to kind of get out in the community. Meet other fellow entrepreneurs that are either from the area or traveling through the area, whether it be from Japan, Europe, you name it. We have people that come out from really all over the world to do this. And we have them every 2 to 3 weeks. Our next one's actually going to be next Friday on the 22nd of September. They are from 8 to 11 p.m. for those who are familiar with the Hyatt Regency Hotel. It's in Santa Clara, also by Levi's Stadium and the Santa Clara Convention Center, for those who aren't familiar. Again, I do recommend it. They are free events. We meet in the front lobby. They're really casual, no topics, and no central topic is there. It's just really a mixing and mingling event, getting to meet new friends, partners, clients, you name it. So again, the next one's going to be on the 22nd of September, 8 to 11 p.m. at the Hyatt Regency in Santa Clara. Hope to see you there.
With regard to value, it's important that we provide value at each and every one of our events. Not just value for your money, which is important because we know many entrepreneurs are struggling financially, so we make sure our events are affordable. And if you cannot afford the cover charge for whatever reason, just come see me. We're always looking for team members to help us out with our events. All our team members can attend all of our events for free, and there are lots of other benefits to being a team member. And we make sure that we provide a decent buffet meal at each and every one of our events. Was this a decent buffet meal? I'm glad somebody likes it. Anyway, we do our best. More importantly, though, at each and every one of our events, it's important that we provide value for your time, which is your most valuable resource. Anyone here getting any younger? Just checking. So when you invest your valuable time to come to our events, we want to make sure that you maximize your ROI. We have many, many partners that help us do what we do. Law firms, venture capital firms, angel investor groups, incubators, accelerators, colleges, universities. Lots of other players in Silicon Valley. Tonight, we're grateful to Datati Digital Marketing for hosting us at this beautiful venue. Is this a beautiful venue? Okay. We've held many, many events here, and we look forward to many, many more. They're a great partner, and we're honored and privileged to be collaborating with them. So I'd like to have Philip, the CEO of Datati Digital Marketing, come up and say a few words. Let's hear it for Philip.
Thanks, Rob. I'm CEO of Datati Digital Marketing. We're focused on helping small to mid-sized companies with their marketing strategy and their basically the digital marketing strategy and the implementation of that. So it'd be websites, brand development, content for your web strategies, and we also do assist with marketing automation tool integration and the strategies and implementation of that as well. So if anybody has any questions about that, feel free to contact me afterwards. Thanks, Rob.
Though our local mission is to support entrepreneurs here in Silicon Valley, our greater mission, though, is to democratize entrepreneurship and innovation all around the world. To that end, we have a robust YouTube channel, youtube.com/idea-to-IPO, so please go check it out. We've documented and archived many of our events, and this rich, valuable content is available on demand, anytime, anywhere, totally free of charge. Whether you're in Sunnyvale, Palo Alto, San Francisco, Maui, Moscow, or Timbuktu. Our partner in this endeavor is Tim Jeggers of Jeggers Films, one of the top professional videographers in all of Silicon Valley. Let's hear it for Tim.
Thank you, Rob. Thank you, everybody. So I'm Tim. I've been doing videography in the Bay Area for around 10 years. I started doing weddings, and then I spanned out to doing corporate events, covering talks like this, and a multitude of other things as well. So if you have any questions about video production or anything like that, feel free to talk to me later. I'll be in the back pretty much all night. And yeah, thanks for coming, and get it back to Rob and get this thing going. Thank you.
All right, without further ado, we'll get started with our presentation. Our featured speaker tonight is a technologist, a leader in this field, an entrepreneur. Most importantly, he's passionate about helping entrepreneurs succeed. So here's the schedule for the rest of the evening, by the way. So we're going to have Alex present until 8 p.m. Hold your questions from 8 to 8:30. We're going to take audience questions. We're going to have a microphone set up. We'd like to have you walk up to the microphone and ask your questions, and we'll try and take as many questions as possible. We'll break at about 8:30, and we'll have more network until about 9 o'clock. So, ladies and gentlemen, let's hear it for Alex Siplican.
Thank you, Rob. Let me check that the microphone is working. Thank you. Thank you, Philip. So my name is Alex. Thank you very much for coming. My goal today is to lay some ground for you in deep learning and machine learning and all the AI stuff that is going on. What's inside, what can be done with it, what are the barriers to entry, and how can entrepreneurs and companies overcome those barriers. I've been in data science for 15 years, building consumer and enterprise products. I'm PhD in speech biometrics, which is teaching a computer to understand who is speaking. And I'm the chief operating monster of Data Monsters, a consulting company doing custom machine learning projects, partnering with NVIDIA and IBM, working for Intel and Cisco, etc. So deep learning in 3 slides. Number 1, deep learning refers simply to artificial neural networks that have more than one hidden layer. If you look at this picture, there is a kind of chart of a neural network that consists of input layer, hidden layers. In this case, there are 2, so it's already a deep neural network. And then the output layer of units. People call them neurons sometimes. So if you see a neural network that have 2 or more layers, this is deep learning. Deep learning outperforms traditional classic machine learning in specific areas when you have a lot of training data where you give examples to the machine and making the machine to understand how to infer those results from the incoming input data. So deep learning was strong is shown to be strong for images, text, sounds, time series, and other things. And number 3, deep learning requires a lot of compute, because to train a neural network, you need to understand the weights, the parameters of the model, and there is a lot of those parameters. And you need a lot of compute power to find the right parameters to work on your data. So these are the 3 things that basically define the deep learning at a very, very high level. On the landscape of artificial intelligence, many people confuse and say that AI, artificial intelligence, is somewhere within deep learning. But historically, AI is much larger than even machine learning. So this is a diagram from a book by Jan Goodfellow. And you can see that AI is the larger circle in this area. And AI can be rule-based, expert knowledge systems that help people without machine learning. Machine learning would be in this second circle. And machine learning, as you would know, is about training a machine to make inference, make predictions on the data, provide some results without writing an explicit program for the machine. So you just throw the data at the algorithm, and it figures out by itself how to get from inputs to outputs. And deep learning on this chart is here inside. So it's within machine learning. It's a kind of machine learning that is specific to neural networks and neural networks that have 2 layers or more. So deep learning is a part of AI, but AI is much, much larger historically.
What is representation learning?
Sorry?
Representation learning between machine learning and what is the representation learning you had out of second there?
I'll cover it later on the slide. So some classic tasks for the classic machine learning are classification, when you present a set of data to the algorithm and ask the algorithm to classify, for example, men versus women by their behavior on the website, or spam versus not spam by email body, etc. Number 2, regression, which is predicting a continuous value, continuous variable. What will be your sales over the next month, or what amount of cash you need to put in an ATM so that it doesn't run out of cash but doesn't have too much cash in it, etc. Many applications here. Clusterization, without being given a specific set of labels on the training set of data, try to separate the data, separate the objects that we observe into meaningful classes. Maybe these would be groups of your website visitors that you want to treat differently, and you want to send personalized emails to those groups without actually knowing what people are in a specific group. You just know that they are different enough to treat them differently.
Just on the question on the regression, does our data that we input have to be normalized, or it could be non-normal data?
Depending on the algorithm. I suggest that if you could, we would ask you, for the purpose of videotaping, to ask the questions after the presentation. Just put them down. I'll be happy to answer. And 2 more tasks that are typical for the classic machine learning is ranking, number 4, and recommendations. They're quite similar. It's about maximizing a function over a set of data based on the history that we have observed. For example, click probability for an ad unit, or relevance to a search request. Recommendations, recommending pieces of content or products to the users based on the user behavior or previous ratings made by this user, or similarity to some other users that behave in a similar way. The most important thing for classic machine learning is not only the data, but the features, the parameters of the objects that you observe, that you feed into the model. The better you understand what is important to make predictions or classification, the better your algorithm will perform. So a lot of the work that data scientists put and worked on were selecting the right features. And the features can be either extracted from the data as is, for example, age, price, number of purchases for a customer of an e-commerce website. Can be invented specifically for a domain based on the domain intuition of the experts that work in this domain. Like, we know that a customer might churn, might leave our company if they call the support center too many times over the last 3 months, for example. They're maybe not very satisfied. Or we know that we typically want to feed a logarithm of money into a machine learning algorithm. It works better. So some intuition about the data in the specific domain. And for complex objects like images, for example, or sounds, scientists have been working a lot to invent specific features, very difficult to come up with, like SIFT and HOG for images, or MFCC coefficients for sound. And these features tend to work better for machine learning if fed into an algorithm than other features, for example. So a lot of effort was put by scientists, by researchers, into engineering the features. In deep learning, it's different. Now, many deep learning problems can be solved without engineering the features. The network, in most cases, many cases, can be trained end to end. It will figure out the features on its own. It will understand what features of an image, for example, are important to distinguish dogs versus cats. And those features will be a part of the layers of those neural networks. So with deep learning, researchers, instead of working a lot of engineering the features, can now leave it to the neural network. And this is very, very attractive to the enterprises and other users of machine learning. So to answer the question about representation learning, on this diagram taken from the same book by Young Goodfellow, the rule-based systems, which already an AI, would be on the left. Then the classic machine learning using hand-designed features is second from the left. While these two approaches, deep learning on the right, are able to figure out the features on their own. And they are very different from the two approaches on the left. So in deep learning, as the data propagates through the network extracts simple features and then more complex features that then are used to map from the input data to finally a class or a prediction of the neural network. It's not complicated, but it's very attractive and it's a big jump. Deep learning is a game changer because for researchers and for corporations, in many cases, it can provide higher quality predictions, faster iterations on the data, and in many cases, it's less investment because you spend less time engineering features. You can use out-of-the-box architectures of the neural network. And deep learning uses raw data as inputs. It can be pixels or sonograms or Mel frequency coefficients, but still it's very standard, or words or characters for text. And it allows end-to-end learning, so you go, a neural network gets you directly from pixels as inputs to categories as outputs. So you don't have to create any rules about how to translate the corners of objects that you found on an image into an inference whether it's a dog or a cat. So end-to-end makes it very less of investment in many cases. Let me touch a little bit on the history of AI just to show that it's been around for a while. Deep learning and neural networks appeared about 72 years ago, 75 years ago almost. By McCulloch-Pitts, in 1933, they've introduced a binary threshold neuron that is still used in some models. Then Hebb, with Hebb's learning, talked about how neurons adapt to the learning situations inside our brain or brain of animals. Marvin Minsky and Dean Edmonds in 1950 built the first computer that had 40 neurons and 3,000 vacuum tubes. And at the same time, Alan Turing proposed his famous test. We have seen that many ideas that are used now in deep learning have been reinvented multiple times or have been staging for long for some reason. For example, the multi-layer network, they've been invented several times in 1980s. CNNs, convolutional neural networks, which are very popular now for image processing, were invented also in 1980. Recurrent neural networks, about the same time. And LSTMs that are widely used for translation by Google appeared or were presented in 1997. So it's been quite a timeline to get here. And deep learning started a while ago. It's a deep history of deep learning. And we have seen a lot of, I'll send the deck. No worries, you don't have to take pictures of it. So we have seen, or the world has seen several AI winters because the expectations of what neural networks or AI or machines will be capable of soon were very, excessive. For example, you can see these quotes. 1956, John McCarthy. We think that a significant advance can be made in these problems if a group of scientists work on it together for a summer. 1965, Herbert Simon. Machines will be capable within 20 years of doing any work that a man can do. So I think now we're getting a little bit closer to that. But at that time, 1985, it was a beginning of a new AI winter. People did not trust neural networks anymore. And neural networks and deep neural networks became powerful when larger data sets became available, which is about 2001. While for the previous 60 years, people had put most of their efforts into algorithms, while now we have seen that more data can be even more efficient if you use an old algorithm with that larger amount of data. And this is a nice spreadsheet that shows that basically the availability of algorithm versus the breakthrough. It took typically 18 years to get to a breakthrough versus data set to breakthrough 3 years. So data is actually critical for deep learning. This is a picture showing that deep learning for speech recognition has seen some impressive improvements when larger data sets plus deep neural networks have become available. 2 months ago, Google had published an interesting research. They have shown that even if we have very, very many images, and Google used 300 million images in this research, we still do not see a plateau in the curve of the mean average precision for this data set. So we can think that the more images we throw on at the algorithm, the higher the precision will be. So there is it brings even more excitement to deep learning. Well, people started looking at deep learning when we have seen a set of breakthroughs where machines outperformed humans for some narrow tasks. This was probably the first one, 2011. Jürgen Schmidhuber had achieved an impressive result of road sign recognition. It's 2 times better than a typical human. And the academia society community was impressed by that. Number 2, straight numbers by Google also outperformed humans by a little bit. And it is getting better and better over years since then. Number 3, ImageNet, held or initiated by Stanford, has seen a very impressive improvement 2011 to 2012. In 2011, the winning algorithm was not based on deep learning. It was a so-called shallow algorithm. Versus 2012, it was Alex Krzyzewski with AlexNet. And if you compare the drop of error 2010 to 2011 versus 2011, 2012, you will see that it's not 3%, but it's about 9%. And that was very, very impressive. And in 2015, neural networks have shown superior performance to human average rate of image recognition. It's also interesting to see the number of layers that researchers put in neural networks. In 2015, it went up from 8 to 152 layers. The more layers they put in a neural network, if it's the right architecture, the higher is the efficiency. So you need more layers and more data. This is the intuition behind it. Some of the interesting cases that the machine, given a set of images, was making. GT stands here for ground truth, the true label for an image. And on this slide, you can see that the machine was right. Even I wouldn't be able to be very sure about the race of this dog or those flowers. But the machine was trained to recognize those objects, and it succeeded. Some error cases are also quite impressive. You can see that the spotlight on the top images can actually be, the classes that the machine came up with for those images were not specifically spotlight, but they're quite close or can be true. A person would hesitate to tag those images in a different way. So I wouldn't call it a huge error in these cases, as well as here. The ground truth is restaurant, but there is a wine bottle and a candle and a plate and a meatloaf. However, neural networks, we have to use them cautiously because they have been shown to make mistakes that can be dangerous for humans. For example, in this research, in this paper by Google, what they did, they trained a neural network to recognize animals, for example, panda. And the initial image of panda gave this probability, this confidence. Then they have engineered a noise image that was added to the initial image with a very tiny proportion. So it's just a very, very light mask on top of this image. And the neural network got it completely wrong. It was, with 99% confidence, completely different animal. And it is known that machine learning system can be, well, spoofed in, by using reverse engineering of the data. So we have to be very cautious about that. These are the three things that made deep learning successful as we see it now. The algorithms, the amount of data, and the amount of compute available now, which is mostly GPUs. Regarding the data and compute, if we take one of the first successful convolutional neural network in 1998 by Jan LeCun, it was working on a data set of 10 to the power of 7 pixels, and it was running on approximately 10 to the power of 6 transistors. 2012, AlexNet, that won the ImageNet competition, was many more pixels and many more transistors. So more data and more compute gave the power to deep learning. But still, there is a way to go, because if AlexNet had about 650,000 neurons, a human has 100 billion neurons. And a bee would have approximately 10 to the power of 6 neurons. So we now are making neural networks that are good at a very narrow tasks. They can outperform humans at specific tasks, but I would say it's early to say that AI is going to overtake the world. But it will change it. Deep learning will change industries significantly. Regarding more compute, in 2010, Istituto sull'Intelligenza Artificiale, Artificial Intelligence Institute in Switzerland, had shown that GPUs are very good for deep learning. They've achieved more than 50 times speed up for training neural networks over CPUs. And this is because GPUs have thousands of cores versus a few cores on CPU. And they can run computations in parallel. And it's like tens of thousands of computations. And it's interesting. This is a slide, a picture from the recent NVIDIA's conference, GTC in May this year. GPU performance is growing 50% year to year, and CPUs are plateauing. So to make more computations, we need to switch our algorithms and use GPUs with those massive parallel computations. The tasks that deep learning is currently strong at include speech, images, and video, and these would be classification and localization of an object in an image, for example, And we have seen that deep learning outperformed humans in this. Also, there is a problem called semantic segmentation when you're asking a machine to say specifically which pixels belong to which object. And the machine will be saying, this is a human, this is a machine, a car, this is a broccoli, this is a plate. Also style transfer, image to image, image generation, perception for robots. I'll show you some examples of these later. Deep learning is also great at text and natural language processing, and it's evolving. It's getting better and better. There is active research and development on that in academia. And we have seen wonderful things, question answering machine dialogue systems using all kinds of embeddings and models. And number 3 is reinforcement learning. We have seen a computer to play Atari games and Go and Dota and several other things. Some of the emerging tasks would be including several modalities in the model and in the system. For example, putting together image and text and asking the machine to give a caption automatically for an image, or searching web by image, or describing a video, what's happening in the video, for example, or answering questions given a picture, recognizing speech augmented by the video, with, where we can observe lip movements, for example, etc. And potentially we will see some kind of common representation for many or all modalities that can be around there. Some kind of thought vectors that people will be combining to come up with deep neural networks solving problems in different areas with different kinds of data. We have also seen that neural networks designed to process images have been used successfully to process different kinds of data, for example, texts or speech or time series, and vice versa. Recurrent neural networks created for sequences were used to process images. So some kind of convergence here as well. There are a lot of architectures of neural networks. And there is that trade between feature engineering in classic machine learning versus architecture engineering in deep learning. To get to the solution of your problem, you have to understand what architecture of neural network you can use for this specific case. And it's not an easy task to solve. So instead of engineering features, we are now engineering neural networks. And this is a barrier to enter this field. Also, you would need a lot of data to train a deep neural network. It's about 1,000 samples, 1,000 examples of objects per class if you want to train a neural network. You need a lot of compute power to train it because a neural network means a lot of parameters and a lot of computations to find those parameters. And that expertise to come up with the right architecture of the deep neural network. But many companies, in many cases, can overcome those barriers. For example, if you don't have enough data in your case and you're working on images, you can use the thing called transfer learning that requires less images per class. And in this case, you train or you use an out-of-the-box neural network pre-trained on a very, very large data set. And you retrain the neural network slightly on your data set, ripping off the final 1 or 2 layers of the neural network so that those layers will be specific to your data set. Many data sets are publicly available, and there are vendors that are willing to work for you to collect and label the data set for you, for your specific case. Regarding compute power, again, transfer learning requires much less compute to get to the result. And if you do not have GPUs, a lot of GPUs in-house, you can go to AWS, Amazon Web Services, and rent instances there. Also, NVIDIA is coming with their own GPU cloud this fall, hopefully this month. And there are many other opportunities to do that. And expertise in deep neural network architectures can be not the strict requirement in many cases, because most of the problems have been solved previously. And in many cases, you can just take an off-the-shelf architecture for your task, and it will work good enough to provide a good ROI for your case. A few slides on how neural networks work. So the artificial neural networks are inspired by the brain, by our understanding of how the brain works. So in the brain, there are neurons, the real neurons. They have dendrites bringing incoming signals from other neurons or from other sources into the cell body that processes that information and outputs some kind of signal through axon. And on the ends, you have muscles or other neurons that will continue processing the information. So taking that inspiration, researchers came up with an artificial neuron. Well, in real life, real neurons are much more complicated than that model. But let's simplify that. So again, input signals weighted with specific weights coming into the cell body, which is just a sum of weighted input signals. We have x0, x1, x2 as the input values to the neuron, weighting them with W1, W2, plus some bias that we'll learn from the data. And then we apply a function, so-called activation function, to this weighted sum of input values. So the output of the artificial neuron is the value of this activation function that is given this weighted sum of input values. By combining these neurons and putting them in layers, we obtain artificial neural networks. These activation functions can look like this, getting from 0 to 1. And there are many other activation functions that researchers came up with. Some of them are hard to train, for example, this one. Some are easier to train in terms of compute power you need. For example, this is really popular. You have 0 if the weighted sum is on the left-hand side, and you have x for the right-hand side. This is one of the parts of the skill sets that a data scientist will need to deal with neural networks. So architectures, activation functions, and some more than this. This is how people represent neural networks. Input layers, so this would be, for example, number of bedrooms in a house. This would be square feet. This would be something else. And these inputs go to these artificial neurons in the hidden layer, and there can be several hidden layers, and those come into the output layer, which is also an activation function. And we output what we want the neural network to output for us. For example, a class similarity. There is an algorithm to calculate the outputs of neural network and train the neural network on your training data set called forward propagation and back propagation. Very simple. To calculate the output of the neural network, you just use the weights that connect the inputs to this artificial neuron and calculate the output of the activation function and so on. It gets to the ending point. You calculate the output of the final layer, of the output layer of the neural network. It's the same weighted sum of inputs here. And to train a neural network, you use backpropagation. You calculate the delta, the difference between what the neural network gave you for this object versus what you wanted it to give. And you use that information to recalculate the weights of the neural network. So you propagate this delta and calculate deltas for all the units within the neural network, and you adjust the weights slightly on every step after you present every element to the neural network. And there is some math behind it. If you will be doing deep learning yourself, you don't need to think about it because there are high-level libraries that take care of all of that. You just need to understand what you want to be doing with neural networks and what architecture you need. An important concept also is the loss function. You need to classify objects, or you need to predict house prices. So you introduce how bad is your model, your artificial neural network on this task. The further the results are from what you wanted, the higher is the loss. And the optimization goal is to minimize the loss that you have. And there are different kinds of loss function. This one would be for classification, this one cross entropy, for example. There are complicated loss functions that have shown to be very efficient for speech recognition, for example, like CDC for sequence to sequence. It's important to choose the right loss function when you are architecturing a neural network. So this would be number 3. Architecture, activation functions, loss functions. So a typical deep feed-forward neural network would look something like this. You have several hidden layers with all the inputs connected to the neurons, the units on the first layer. Sorry. Then the units from the first layer are connected to the second layer. Every neuron is connected to each neuron on the second layer, and vice, etc. So there is a problem with this configuration. It works well for classification, but if you want to train this neural network, you'll have to deal with a lot of parameters. For example, if you will be processing images, 100 by 100 images, and you will put just 3 hidden layers with 100 neurons each, it will be over 1 million parameters. So the model potentially will be too complicated for this task. And actually, we have seen that going deeper than 3 layers for these feed-forward neural networks rarely helps. It does not increase accuracy. So researchers, Jan LeCun, came up with convolutional neural networks, a different architecture that has been proven to work really well for images. It works differently. Instead of having all the neurons of the next layer connected to all the neurons units on the previous layer, there is a fixed set of weights that connect this specific unit to a specific segment, a square on the previous layer. And all the other units here share the same weights. So, for example, in this case, there will be only 4 by 4, 16 weights for the entire next layer of the neural network. If we look a little bit deeper, the element on the next layer will calculate its value by applying this matrix to the previous layer. And this matrix will be dragged from left to right through the pixels of the input image, for example. And only 9 weights will be used to compose the next layer, which is much less than in feed-forward neural networks. And for AlexNet, the activations of these units on the next layers, when presented an image of a cat, have been shown some interesting patterns here. The first layer, the 5th layer. So apparently the neural network was detecting some kind of features on an image. And the weights of those matrices seem to be looking for some patterns in the images, maybe some corners or some changes in the structure of images. The neural network came up with these patterns automatically. And this is a huge breakthrough and an advantage of deep learning. The typical set of layers used for convolutional neural networks include convolutional layer, pooling layer, which just takes a maximum among several pixels on the previous layer and outputs it to the next stage. And a set of fully connected layers, those that we have seen for the feed-forward neural network at the end of the neural network. And the outputs can be, for example, classes of objects that are detected in a picture. There is another class of tasks that we want to solve. These are the typical use cases for CNNs, convolutional neural networks. What's in the image, where the object is, emotions of people, self-driving cars, object detection, and semantic segmentation for images. Broccoli, carrot, etc. For time series, people had been using so-called recurrent neural networks. It's a similar concept, but these neural networks are aware of time. So they observe a sequence of data in time. And the neurons inside the hidden layer are connected to neurons inside the same hidden layer at the next time step. it can be depicted like this. So we have observed some object at t-1 time step. We have calculated the outputs of these hidden units. And the outputs of these hidden units serve as inputs to the same hidden units at the next time step. In this case, these neural networks are capable of modeling complicated processes and have been used to do speech recognition, for example. So they can keep memory about what happened in the past and remember it later to come up with some kind of inference. But there is a problem with these neural networks, so-called vanishing gradients. The longer the sequence that we present to a neural network, the higher is the chance that the neural network will not be able to remember what happened before. Well, shown by the gray color on this picture. To deal with that, people, Jürgen Schmidhuber had invented so-called LSTMs, long short-term memory neural networks. They are capable of keeping the information inside the network and remembering, bringing that information back when they think it's needed. And if you want, I will be able to discuss the structure later. Sometimes when you know the entire phrase and you want to understand what parts of speech are inside the phrase, you can use so-called bidirectional LSTMs. The notion of time goes both forward and backward in this layer. So we have some information about the future to understand what we're observing right now. Some of the use cases of neural networks. Memory-based and attention-based. For example, a neural network was presented with a set of phrases about what happened, who has done what, and asked a question and answered it correctly. Or has been presented a picture and asked a question about the picture, what kind of trees in the background. Many people use Google Translate, and it's an example of neural machine translation. And it's getting closer to the perfect translation score for many languages. And Google uses LSTMs in their models. Image captioning, asking a machine to describe what's in an image, is also a very interesting case. Image colorization, being trained on different images. A neural network is capable of coming up with colors for a black and white image. That seem to be quite reasonable in many cases. Winning a very complicated game. Google DeepMind, we've seen that a year ago. Driverless cars, observing the surroundings in real time and processing gigabytes of data. Dense captioning, what's in an image at a very high detail level. Style transfer, presented being presented an image taken with a camera and an artwork. The neural network was able to come up with some kind of fusion of the artistic style and the original picture. Neural networks that can generate images, being trained on a lot of images of volcanoes, for example. It can be generating other new volcanoes that have not been seen by the neural network. Or being presented with a phrase describing what we want to see in a picture. Neural networks, this one was able to generate, for example, a bird completely red with black wings and pointy beak. These are the images that did not exist before the network generated it. And this one is a funny example of a robot training itself to do some tasks in the physical world completely by try and failure method. And in Berkeley, they've used reinforcement learning to do that. In the industries, companies have been using neural networks and deep learning as well. So, so far we have seen computer vision being used or tried to identify distracted drivers by insurance companies, or to help drivers involved in a car accident to quickly assess their damage without having a person to come on site, or a virtual assistant to assist agents of an insurance company and to educate those agents on insurance products of that company. In retail, brick and mortar stores detect suspicious behavior of visitors of the store, of shoppers, whether someone is putting something in their shirt or backpack, gather information about demographics and behavior patterns in store, and generate real-time estimates of the products at the store by observing the displays at the store. At sports, for example, translate raw data into narratives for baseball, for example, or track players in video streams, or creating video highlights of a match for tennis. So the conclusion is that deep learning leads to automation on steroids. This is a quote from Andrew Ng. And I would not say that AI is about to conquer the world, but entire industries will change, and deep learning is a critical competitive advantage for businesses. I have included several links into the presentation if you will want to dive deeper and take some courses on deep learning. These are the resources, blogs, and Twitter accounts to follow. And thank you. Email me for the slide deck.
Let's hear it for Alex. So at this point, we'd like to take as many questions as possible. If you have a question, just come on up, use the microphone, and ask away. Who's got a question? Go for it.
Hi. Thanks for that presentation. That was pretty good.
Yep.
On the example of the panda, and you had a
Yep.
overlay, why would the neural network get confused with that? Wouldn't it be similar to a badly taken picture of a panda?
No, you see, the difference is not seen, cannot be seen by a human eye between the distorted image and the original image. To a human, it's basically the same image, but the neural network is vulnerable to these changes. The weights of the neural network and the way the network looks at this image is sensitive to these tiny differences between pixels. So the interesting thing here is that we humans do not see the difference, but it's critical for a neural network, and that is a red flag for us. Thank you.
So on the video, how much of that sensing was done with visual light, or ambient light, or radar light, lidar kind of sensing, and how sensitive is that to the ambient light versus using a standardized light source?
Can you give me a use case?
Well,
What
let's
are you
say
trying to accomplish?
the simple one, square peg in a round hole with the box. How much of that was, using laser lidar sensing versus, just whatever ambient visible light was there and regular cameras viewing the scene to sense and interpret?
And what's the device that is observing the scenery?
Well, you had the video, right? In your video?
Oh, those robots.
Yeah, where they're putting, basically the square peg in the round hole kind of
Yeah.
demonstration.
So I'm not sure what kind of device did they use in this case specifically. I know that in some of these experiments they've used regular cameras. I'm not sure about this specific case, but I have put a link to this work here at the bottom of the slide, so you'll be able to find out.
Okay, yeah, it's kind of a vested question for me because I make lights. And we found robotic vision systems are particularly sensitive to for increasing the visual dexterity that the robotic systems have when you have a uniform, even light, as compared to unknown ambient light that can cast unknown shadows.
Yeah, it would make sense to connect with that lab at Berkeley to discuss that,
Thank you.
because they would be the experts.
So given the state of the art of artificial intelligence, obviously we are in the year 2 of a 20-year cycle. It's going to take quite some time. So right now, in your opinion, what are the 3 segments, for example, machine vision, natural language processing, cars, which are the top segments that people are gravitating to get results? Question 1. Question 2 is, for every input, there's a weighting factor to go with it, and then there's a bias. How do you determine the weighting fraction, the weighting that goes along with the input? There's maybe you can explain a little bit more about this weighting function along with the input, and then there's of course the hidden. The hidden is where all the algorithms lie. So maybe you can elaborate a little bit more on those.
So regarding the 3 areas that will be progressing in the next few years, well, I would love to see self-driving cars coming. And I think, with the new regulation, it should be within 3 years, potentially. Regarding computer vision, there are quite impressive advances. Like in May, researchers have published a paper describing an end-to-end architecture that is capable to doing 3 things at the same time. Detecting where objects are located in an image, tagging those objects, and applying or extracting the mask of the object from the image, which pixel corresponds to an object, which is not. And a lot of progress is being made with conversational systems, virtual assistants. The problem of generating text is not solved yet. It would be exciting to see it solved. Currently, all the virtual assistants use templates to answer to the requests of the customers. And potentially, attention-based mechanisms for for text processing and for image processing will also be powerful, and we'll see some changes in both academia and commercial applications coming out of neural networks that use that mechanism. So the weights of neural network, that would be quite a discussion. Were you talking about these weights?
Yeah, typically, I mean, in general, you have shown a lot of these models, and there's every time there's an input, there's a weighting function to go along with it, or weighting to go along with the x and w, and then you have the hidden functions, which is all the algorithms which are going to act on it. So, for example, like you said, example of everybody can hear. Example of when I get my property assessed by the county, yeah, when I get a property assessed by the county, and it happens every year, so they look at the nearby, but they don't have a very good algorithm whatsoever. So something like this would help them to get a better assessment of each and every property for the assessor, because you have to look at so many other factors which they don't look at this time. They have just square foot of lot and a square foot of building, and that's it. So if you were their advisor, how would you go about telling them?
Well, if they have a lot of data, then they could use complicated models like deep neural networks to do that. And the benefit of using machine learning and deep learning is that the model is able to take into account thousands of parameters. A human would not be able to do that. So that could be a good application. Well, the weights...
See, because the input is the price of that particular property, and the weighting function is square foot of the building is a weighting function.
no,
and where is it, the zip code it's located. So there's so many, I'm just trying to see, how do you approach some problem like this if you were to advise them?
Let us discuss this after the Q&A session.
Sure.
Thank you.
Hi. This is Swami. I have a question regarding the IBM Watson.
IBM Watson?
Watson? Yeah. So how it is different from this deep learning? Is it the same or? And then the second question is, you explained so many algorithms, CNN, RCNN, RNN, etc. I was not able to understand which one is better for what scenario.
Which one is better for what?
Scenarios, like use cases.
Scenario?
Yeah. Like CNN is best for the images, or RNN is better for the speeches, or which one is, where do you think is where we can apply the best one for the?
Where we can apply the best, could you speak a little
Yeah,
louder?
which algorithm is best for the which use case?
Well, regarding IBM Watson, that's a very large system. It has a lot of components. IBM has a set of building blocks. They call it Bluemix. And Watson it can be thought of as a set of bundles combined of the building blocks that Bluemix offers, and trained or fine-tuned for specific domains. So Watson has been around for many years, and in some cases Watson has been used successfully, but for several reasons on our projects we rarely use Watson. For example, Watson has a capability to be used for virtual assistants. We think it's a little bit too complicated to train Watson, to program the intents and the entity extraction in Watson compared to some other solutions that are out there for that specific problem. So we did use Watson, but only a little piece of it. So if you have a use case that was well covered by Watson, you should consider using that. Otherwise, potentially it will be another third-party solution or a custom-built solution. Regarding use cases, scenarios, and architectures, I wouldn't have an answer because there are too many use cases and too many architectures of neural networks. If you give me some specific case, probably I could think of something.
Yeah, for example, diagnosing the, diabetes.
Sorry.
Sorry, okay. Yeah, the diabetes disease diagnosis and measuring the the effect on the how it is propagating, at what stage it is, and those kind of things.
Mm-hmm.
Which one we
So
can use that?
it depends on the amount of data that you have and on the specificity of the features that you can observe. In many cases, you do not need neural networks and deep learning to solve that. In many cases, techniques like random forest or XGBoost would be good enough, much less complicated, much easier to train, much less data required. So I would suggest to be cautious about deep learning. And we can discuss a specific use case again.
It's a question about discussion about one of the challenges of machine learning these days is around the black box problem.
Mm-hmm.
That is, the algorithm trains itself. You're not really aware of how it's training itself, and that maybe some cases that's more of a problem than others. First question is that a feature of deep learning as much as it is for machine learning in general, or is there a difference? And second, where would you say that is more of a problem? I mean, from looking at the examples you gave, it occurred to me that maybe where the delta is more easily measured, you sort of can very easily determine if it gives you a false positive or false negative, then maybe it's not such a problem, whereas one of the use cases you gave was looking at shoppers in a retail space and figuring out who looks suspicious. And maybe it's a little harder to know after the fact whether you are fairly or unfairly profiling people. So the black box problem might become more of an issue. But just curious, those two is how much does it relate to deep learning as well as machine learning in specific, broadly, and in what circumstances do you see it as sort of more of an issue in terms of application?
Thank you. So this is a very good question. The interpretability of the results of machine learning is a large topic. Some of the machine learning models can be, well, the results can be interpreted. For example, decision trees. Well, the decision trees, when they're trained, they work in a very straightforward way. They take into account different parameters that we observe, and they make decisions based on those parameters, one decision at a time. Whether we see that the temperature outside is below or above 100 degrees, for example. Whether it's raining or not raining, etc. And we come to a decision whether we'll have success during baseball today or not. We can track the reasoning of the machine back to the initial level. So some of the models allow us to do that. many of the models do not allow doing that. For example, random forests or neural networks. And there are two ideas about that. First of all, the results of inference of a neural network. If a neural network had predicted something for an object, we could understand what, or try to understand what made the model predict this outcome by varying the features, the parameters of the object, and trying to understand whether we observe this feature or we do not observe this feature. What will be the output of the model? When we see that specific features were important to getting to that decision, we can say that this is because the black box came up with this conclusion, this prediction. And number two, I know that there are two approaches, like metaphysical approaches to black boxes and machine learning. More of a European style approach is if a machine learning model is to make significant decisions, it must be interpretable. And in the US, we have to trust the black box, even if it has been trained on some data that contain correlations versus causations. While the outputs are bringing return on investment, we are good to use it. So, and there are discussions about that. And at Berkeley, Stuart Russell now is leading one of the organizations for ethical AI and how we should be dealing with AI and how, how cautious we should be about interpretability. So this is a huge topic. Thank you.
I just have a question on what are some of the security issues that might come up with, say, implementing system like this. And I'm just thinking the use case that comes to mind is like a lot of stock trading actually is done by machines today. And I'm sure there are machine learning and deep learning involved in some of those decisions, right? So is there any kind of a way or an incident that that comes to your mind that actually has influenced a decision either way, and how somebody can kind of, when they're designing this system, what they need to be aware of, and putting this all together from a security point of view?
Well, the security is about attacks and threats and detecting those attacks and threats and identity thefts, for example. This is, it seems to be different from stock trading, for example. When machines trade stocks, well, I know people who have clusters of GPUs at their home and doing a lot of transactions per minute. But, well, this is a separate issue from security. Is there anything specific for in security that you would like to discuss?
I'm just looking for general guideline or your kind of, from your experience, if you want to share that, something that we need to be kind of mindful about. Yeah.
Okay. So, for example, in access management system or some other systems dealing with security, when the risk can be very high. In some cases, when the confidence is not high enough, the confidence of the automated reply of the machine learning model, and the risk is high, you will want to put a human in the loop to assess the decision of the machine. So in many cases, the machine will be able to handle the situation automatically if the risk is not very high and the confidence of the machine is high. So it will be a good trade-off between lowering the costs and lowering the risk when using machine learning. Does this answer your question?
Yeah.
Okay, well, I'll be able to discuss later.
Hello. I was curious, like, aside from security, what other knowledge-based jobs do you think would be affected by deep learning?
What?
What other knowledge-based jobs besides security do you think could be affected by deep learning? And I guess, like, how long do you think that would probably be an issue? Like, how long would it take before that actually becomes an issue for those jobs?
Well, I remember last November, Accenture had made a presentation regarding the kinds of jobs and industries that will be affected by artificial intelligence. As far as I remember, they predicted that knowledge-based jobs are not on the first line of attack as of now, but as the systems that are able to answer the questions automatically or to mine the data that tracks the knowledge bases and come up with meaningful replies will emerge probably within the next 3 years. This will be a higher probability. And there are several companies that are working hard on that. Maluba, acquired recently by Microsoft, coming from Canada. Semantic Machines at Berkeley, and also MindMeld in the city. They were acquired recently by Cisco. So I think, well, this is close, but we're not there yet.
Okay.
Hi, thanks for a very insightful presentation, first of all.
Thank you.
I have a question, and you alluded to this in your presentation, but I mean, there's this question about, given the strong effects of in performance of the amount of data that you have, and given that presumably some of the knowledge is owned by as intellectual property, do you foresee a scenario where just a few large, players, state players or companies control basically the field and AI and deep learning, or is there going to be a playing field for regular companies and regular players out there?
Thank you. In many cases, the value of a company comes from the data that it is able to collect. Because the data is, in many cases, unique. And the algorithms, in many cases, are available to the entire community. Because the publications that we see coming from the academia world can be used and applied in different industries, in different companies. But not all the companies would have the data sufficient to train a complicated model like a deep neural network to do that. I would say companies that are able to get a lot of traffic, a lot of customers, a lot of consumers to use their products would be able to collect a lot of data and would be leading the industries. And we clearly see this with Google and Baidu and Facebook, for example. They are leading the AI frontier now in many areas because they have data, they have capital to deploy researchers to work on the data, coming up with new algorithms as well. So I would say this will be correlated. When you have data and you have capital, you will be able to be also on the cutting edge of the research. And it's up to the company whether they want to share the results with the community or not. Like Apple was not sharing the research results until like a few months ago. They're making just the first steps to do that. Data is number one, and algorithms are now number two. Thank you.
Yeah, I know we don't have a lot of time. I'm interested in healthcare applications. And I was looking at some of the machine learning, and it looks like deep learning might also have an application, specifically with looking at digital health records and looking for underlying patterns of disease that may be present. Have you worked with any healthcare applications where you're looking at taking digital health records and finding more information there?
Yeah, thank you for the question. We have worked with some projects in healthcare. The problem there is that there is little or no training data to train complicated models because of the regulations that exist in this industry. You have to be HIPAA compliant. All the medical records are private, cannot be made available for researchers. We have worked with a company in San Francisco. They have a goal to solve cancer. So they will start by matching patients based on their medical records and the results of DNA analysis to clinical trials that are available in the US. So they were not able to actually train a machine learning algorithm to work and do the matching automatically. They had to start with building a manual data pipeline to manually process PDFs with medical records, to extract the labels, and then make a conclusion whether a patient is eligible for a trial or not eligible. And later on, when there is enough data, a machine learning model will be able to rank clinical trials for specific patients. The more impressive results have been in the area of computer vision to work on images, MRT images or CT images, for example, to detect whether there is a tumor or there is an anomaly or something else. Like there are many applications and many startups working on that, and some of them have been quite successful. So I would say now, yeah, there is more data available. So NLP and text analysis is the next frontier for healthcare because of the problem with data. Thank you.
Let's give it up for Alex.
Thank you, Rob.
So if you'd like the slides, email Alex directly. The video will be on our YouTube channel in a few weeks, youtube.com/idea@IPO. Alex will stick around for any one-on-one questions. Please finish off the pizza. Thanks for coming, and we'll see you next time.